Yes.
Okay. We are starting on 6.1 today, section 6.1. You remember how to solve something like this? You guys know how to solve something like this, second order differential equation? We learned this already, right? Characteristic equation and then solving it, and then we have done this many times. So we know how to do that. You guys remember how to solve something like this? This one will be using undetermined coefficients. So we also learned that. What technique do we use to solve this type here? The first one is a homogeneous equation, so that is easy. Okay. With constant coefficients. This one is undetermined coefficient. What technique do we use to solve something like this? Can we use undetermined coefficient? The right hand side, if we keep differentiating this, the right hand side, does it stop at somewhere? Does it terminate or repeat?
No.
It doesn't. So we have to use a technique that we learned, I think, in chapter 4 also. What technique do we use? For a problem like this, okay, we will have to use power series. Okay. So this particular chapter that we're going to study is going to use power series to solve this type of problem, or something similar to that. I mean, you can use power series to solve the other problems also, at least some of this. Okay. So the power series, we learned that in we learned this in calculus 2. There are a couple of power series that you probably should kind of know. There's a table of recurrence series in the book, but I don't really need you to memorize the table. Okay. So this guy, I would like you to know. So this is just a geometric series. So this guy will add up, this guy here will add up to 1 over 1 minus x. The absolute value of x is less than 1. Okay. So the interval of convergence is minus 1. Is this coming back to some of you? I hope. Or you just so long ago that you don't remember anything? So I need to.
It was quite some time ago.
Quite some time ago. Sorry. I can quickly go over why this is the case if you want. I mean, this is just means that this is an infinite series, but with a variable in it. So this guy add up together represent this function. Represent this function. Okay. As long as x is between in this interval minus 1 to 1. So what it's saying is that if you put x equal to 1/2 here, then you add all of this up. Okay. Then you get to some number. X equal to 3/4, you put it in, you get into some number. Okay. So this is an approximation of this guy. Okay. So this guy is a function, and this is an approximation of the function. If you take enough term, then it will be exactly equal to this function. You guys understand what this is saying? It's writing this function in terms of a series. Okay. So this function can be represented by a polynomial of infinite degree. Okay. It's a polynomial of infinite degree. Another one is e to the power. Oh, by the way, this guy I can write it in summation notation. Okay. Another one that's somewhat important also is e to the power x. It's 1 plus, I think it's 1 plus x squared over 2 factorial, x cubed over 3 factorial, x4 over 4 factorial, and so on. And the interval of convergence is minus infinity. So everywhere, whatever value of x, e to the power x can be approximated by this in the polynomial of infinite degree. Then there are other ones, sine x, cosine x, and so on. But I don't even expect you to memorize any of this. Okay. But it will be, I myself remember this too, at least. And from this, I can derive a lot of the other ones. I am going to go through an example, a very simple example, using the technique of power series to solve a differential equation. Okay. And I'm going to go very slow on this one. Any questions so far? This particular example, you don't even need to use power series to solve it. But for illustration purpose, Okay, I'm doing it for illustration purpose. You actually know how to solve this already. You have done it so many times. So this is dy dx plus y is equal to 0. Okay. We have learned how to solve this. How do I solve something like this? Forget about this power series for now. Let's try to solve it using the methods we have learned. So we know what the answer should be. Can one of you tell me how to solve this? What technique do we use? No?
Can you just integrate both sides?
You can't.
What do you mean by solving? What do you mean? What are we trying to solve for?
There's a y here. You can treat this as a linear equation, but the way I'm going here, I'm separating the variables.
Oh, variation of parameters?
Huh?
I can just separate it. This is separable, right?
Oh,
You're
okay.
just going to multiply both sides by dx.
Yeah. Okay. dy over y is negative dx. This is basically exponential decay, this one. Right? It's an equation for exponential decay. And then you integrate both sides. So it will be ln(y) equal to negative x plus c1. Oh, that should be the answer. Okay. You guys follow this? Any question? You guys are very quiet today. Okay. So I'm going to solve this using the power series method. Okay.
Okay.
So we write, this is the solution. Okay. Write y equal to some infinite series. Okay. Now this is the solution. It's just that the solution, instead of writing it as a function, we write it as a power series. We write it as a polynomial of infinite degree. And then we try to figure out what this polynomial should be. Okay, that's the idea. Now I'm going to be more explicit. This one is C0 plus C1x plus C2x squared, C2x cubed, and so on. So what would be y prime? Based on this, what would be y prime? Y prime would be, what's the derivative of C0?
0 plus C1 plus 2C2x.
Very good. Is that okay? That's my y prime. Okay. So it say y prime plus y is equal to 0. That's what it says. That means this guy plus this guy should be equal to 0. Okay. So C0 plus C1 plus, when I add this, I'm just adding these terms. This is constant term, this is linear term, this is quadratic stuff, and so on. Okay? C0 plus C1, one entity. C1 plus 2C2 x plus C2 plus 3C3
square plus C3 plus 4C4 x cubed plus, keep going, and then equal to 0. Okay? You guys follow up till here? Yes? Okay.
Yeah, that's good.
Okay. So now you have this polynomial equal to 0. So all the coefficients is going to be equal to 0. Okay. So I have this. And so on. Are these still okay? Yes?
Yeah, you're good.
Okay. So I'm going to express C1 as C in terms of C0. C1 is negative C0. What is C2? C2 will be in terms of C1 here. C2 will be negative C1 over 2. But C1 can be expressed in terms of C0. You guys know what I'm talking about? So what do I end up with? In terms of C0. Minus and minus become plus. So this one will be 1/2. Is that correct? Are you guys still with me? C3 negative C2 over 3. But C2 is this guy, will be negative this guy over 3. Okay, so will be negative this guy divided by 3. C4 will be negative C3 over 4. Will be negative of this guy, the negative and negative become positive. 4, 3, 2. Do you guys see a pattern? Do you guys see a pattern?
Factorial on the bottom.
Okay. So Cn will be some kind of factorial, C0. But then it's alternate, right? Negative, positive, negative, positive. So you will have a negative 1 to the power, either n or n plus 1. We have to figure it out. C1, you put a 1 here. C1 will be negative C0. So negative 1 to the power n is correct. C2 will be positive, right? For the 2 here, minus 1 squared is positive. So this is my Cn. This is my Cn, okay? Now we put this back. I mean, you have never seen this type of technique before, so it's a little bit heavy. So just feel free to ask questions. Okay, so we are going to put this back into here. So my solution is y equal to summation n equal to 0, infinity, Cn xn, but what is Cn? Cn is minus 1 to the power n over n factorial C0. Okay. And this guy, I can take the C0 out. I have the xn here, sorry. Okay, Cn xn. Take the C0 out. Another way to write this is now remember earlier, I probably shouldn't have erased it. I write down e to the power x is summation x to the power n factorial. Okay, so e to the power minus x will be this, minus x to the power n factorial. So what we have here, this guy here is e to the power minus x. So I got my answer. The same as what we did using separation of variable. How are we doing, guys? Am I scaring you?
I think we're okay. It's just a lot of information.
Okay, a lot of information, okay. So let me maybe review it, okay? I'm going to review it. For this type of problem, when we want to find the answer in terms of a power, using a power series method, we will assume the answer, the solution, can be written as a power series. This one is written as a power series. Assume the solution has that form, okay? And then you start to take derivatives and then plug it back into the original equation, okay? To get some relationship between these coefficients, okay? And then you try to relate these coefficients, because when this polynomial equal to 0, that means all these coefficients are 0. All these coefficients are 0, okay? And based on that, you can figure out the relationship between these coefficients, and here will be iteratively compute everything, all the coefficients in terms of the first coefficient, which is C0. And eventually you end up with the answer. Is it okay?
Thank you. That was helpful.
Is it all right? Now I'm going to redo the same problem. Okay. I'm going to redo this. Unfortunately, I don't have a lot of space on the board. Okay, I probably should have planned a slightly better. But I'm going to redo this problem by, instead of writing everything out, because writing this out, I mean, of course, make it easier for you to see. But a lot of times, the way we do it is that we want to make it a little bit more concise. Okay, and we use this summation notation. Okay, so I'm going to essentially redo this column.
Wait.
Okay, sorry.
Let me just see the final.
Yeah.
One second.
No problem. I don't have to go too fast, okay? I have time.
Okay, so I follow all the way up to when you get C4 is equal to C0 over 4 times 3, 4 times 3, 2.
Yeah.
And then you find Cn. What is Cn again?
Cn
is negative 1 to the
term,
n.
the general term.
No, at the bottom, Professor.
Cn will be minus 1 to the power. So this one, you see, this one is 4 factorial. This one is 3 factorial.
Oh.
This one is 2 factorial.
Okay.
So Cn will be n factorial.
Okay, I got it. N factorial. I couldn't quite see that.
Oh, okay. Sorry.
Got it.
It's too low or something?
No. It's just the N was in. I just couldn't see. That's yeah. Okay.
How do we know to assume that it'll fit the power series formula?
You don't have to memorize. I don't expect you to memorize it. Usually at the end, this is your answer. Your answer is this. in a lot of this type of problems, you can't really figure out what the function is. There's no closed form for this. Sometimes this guy is just some power series. Okay? Just like when you'll be learning in calculus 2, you have a power series. It has a radius, it has some region of convergence, so it represents some functions. It doesn't have to be a nice function. Did I answer your question? It's just this particular problem is easy. So we actually get to a form where you can recognize it to be equal to this. Because this problem, we can actually solve it in another way, right? Solve it by separation of variable. You get a nice closed form formula. And that's why this one would be nice. And if you recognize it, you know this is e to the power minus x.
I was asking more about the part in green towards the top. How do we know we can use that formula?
Oh, how can I know that we can use that formula? There are conditions on this, okay? But I'm not going to go into that detailed conditions, okay? But the intuitively, it's a 252 thing. If this guy has some solution, okay? Sometimes the solution is difficult to find using the method we study, okay? But the solution is some solution curve. That solution curve can be represented by a power series in certain region, certain interval of convergence. It's a 252 thing, okay? Where some function, where functions can be represented by as a polynomial of infinite degree. Did I answer your question, Talia?
Yeah.
Okay. So because in 252 we say that, okay, sometimes functions cannot be represented as a polynomial. I mean, of course, a polynomial is nice, but some functions you can write it as a polynomial of infinite degree. So for example, e to the power x is nice, but there are some functions, we actually learned some of them, right? In 252, it converges everywhere, but it doesn't have closed form. I think we learned something called the Basel function. And didn't really learn it in detail, but at least we come across it. Okay. I mean, this occur in engineering. Okay. It will be just like some function. I forgot I don't remember the formula, but it's a bunch of factorials and so on. Okay. We actually talk about whether it converges or diverges and so on at that time. Okay. So we are representing the solution. We're just conceptually thinking the solution as a polynomial of infinite degree. Okay. And then from there, we derived all this relationship between the coefficient of the polynomial. Now, this is very different from what we have been doing, so it's a little bit hard. Okay, so any other question before I redo this problem again? Exactly the same thing, except I just use slightly different notation. Is it all right? Can I go ahead?
Yeah, you're good. You're good.
I am going to try to do it over here, okay? Just use all this remaining space, okay? Because I want to say this, okay? So we want to solve this. So we write y equal to this. So this is really the solution. This is the solution that we are looking for, okay? But we want to determine the Cn, the coefficients. So y prime, I am going to use, I'm going to, instead of writing it out, I'm going to use the summation notation. So when I do this, when I differentiate this term by term, can you guys see that?
the derivative of x to the power n will be n times x to the power n minus 1. Now, typically we start with 1 here. Because you do the y prime, the constant term go to 0. So this you can see it from here, okay? When you take the derivative, the constant term does go to 0, okay? So now we start out with 1 times C1. Is it okay? Now I want to essentially do the same thing, except I just have a different notation, as I said. Okay. So y prime plus y equal to 0. What does that mean? That means these two added together equal to 0. Do you guys still follow?
Yeah.
Now we are trying to combine these two power series. Okay, combine these two polynomials of infinite degree. Now the problem, there's a slight issue here. This is to the power n minus 1. This is to the power n. It's like a little bit inconvenient to combine them. So we're going to shift the dummy variable here, so that I would have x to the power n for both terms. Now this one is nice. I'm not going to touch it. This guy here, okay, this guy here, this next step is kind of not very nice because running out of space. So it's summation. Now here, this step from this to this, I'm going to replace n by n plus 1. So it's really the same as doing this, except here it's more explicit. But when the expression is a lot of stuff going on, you don't want to have to write so much, then you will use this type of technique. So we place n by n plus 1. So this one, the goal is because this one, if n become n plus 1, then you have n plus 1 minus 1, which will be x to the power n, and will line up correctly with this. So n plus 1, Cn plus 1, x to the power n plus 1 minus 1 will be x to the power n. Now here, it was n equal to 1 to infinity. I have to replace n by n minus 1. So everywhere I see an n, I change it to n minus 1. I change it to n plus 1. So this is n plus 1 equal to 1 to infinity. Do you guys still follow?
Yeah.
Okay. So now here, the next line will be, now n plus 1 equal to 1 to infinity. If n plus 1 equal to 1, n will be equal to what? N plus 1 equal to 1 is the same as n equal to
0.
0. Okay. N plus 1 equal to infinity, so n will be still infinity. So this will be n equal to 0 to infinity. So n plus 1, Cn plus 1, xn. I'm going to just writing a lot of redundant stuff because I want you to be able to follow this. Now they line up nicely now, this xn here. So basically you have two polynomials, okay? But this xn line up nicely. So I can actually add them up nicely by adding these coefficients up. Adding this guy up with this guy. So you'll be n equal to 0 to infinity, n plus 1, Cn plus 1 plus Cn x to the power n equal to 0. You still follow this? It's the same as the process here, which I just erased part of it. Yes.
Do you mind going over the replace n by n plus 1 again?
Okay.
I'm having trouble.
I also have a question.
Okay.
When you replace n by n plus 1 for
Yeah.
the first part, why don't you have to replace the second part? Why?
Oh, the whole point is only do this the first part. If I do it only also for the second part, then this one will get to some other exponent.
Right, but why is it okay to not do it first?
Oh, because these are two separate expressions.
Okay.
So this one is one quantity here. So that quantity, I leave it unchanged. Okay. I'm only doing it for the first part, essentially.
Okay.
Yeah, I didn't make it too explicit. Okay. So I'm replacing Shelby. I'm just doing this replacement for the first part, okay? Because the whole point is to bump this guy up a little bit so that they line up. Okay. So when I do, let me just rewrite that part, what I did here, okay? And I will give you some more examples later on doing this step, because this step a lot of students get confused about this step. So this is what I did. I'm saying that this one, okay, here is replace n by n plus 1. Okay. So Shelby, every time I see an n, I change it to n plus 1. Okay. This whole expression. Okay. You can say replace k, but replace n by k plus 1, but then k is just another dummy variable. Eventually become n again. So I actually like to do this a little bit faster, but conceptually it's the same thing. So replace n by n plus 1, then this guy become, now every time you see an n, you change it to n plus 1. Okay, now n plus 1 equal to 1 means n equal to 0. N plus 1. N plus 1. N plus 1 minus 1 is 6. Yeah. Is it okay, Shelby?
Yeah, much better. Thank you.
No problem. Other people okay? Are you guys good?
Yeah.
I'm going to keep going, okay? I mean, I already did it with a little bit more explicit manner, but this way, usually we do it this way because sometimes you have more terms and so on. Okay, if you just keep writing it out, it's kind of difficult to see. You have a lot of writing, but you need to kind of somewhat get good at this replacement technique. Okay, so that you can combine things together. So I am going to keep going on from here. Now here I have a polynomial of infinite degree. I have a polynomial of infinite degree and it's equal to 0. So all the coefficient has to be 0. So this is the coefficient. Okay. So all the coefficients are going to be 0. That means n plus 1, Cn plus 1 plus Cn is equal to 0. Okay. Do you guys follow this step? A polynomial of infinite degree equal to 0, so all the coefficients are 0. Can you guys accept this step? It's pretty intuitive.
Yeah.
Okay. Now, this is called recurrence relation. Now I got a recurrence relation. It's really what I wrote down earlier. Okay. Now this recurrence relation is going to allow me to write Cn plus 1 as in terms of Cn. Okay. I mean, both of these are recurrence relation. I mean, these two are the same thing. Okay. So from the recurrence relation, you can start to write out this stuff. Okay. So when n is equal to 0, so this is for
this is for all the coefficients, right? For all the coefficients for n equal to 0 all the way to infinity. This is for all n. So for n equal to 0, 1, 2, all the way to infinity. Okay, because the coefficient, this polynomial, this x to the power n start with 0 to infinity. So that means now I have this recurrence relation. So what will be when n equal to 0, I will have C1 equal to minus C0 over n equal to 0 over 1, which is minus C0. Okay, and C2, based on this equation, is for n equal to 1. C2 will be minus C1 over 2. Okay, and so on. So C3 will be minus C2 over 3. Okay, and C4 will be minus C3 over 4. But this guy, we can iteratively do this, right? Now this guy is minus C1 over 2. But C1 is minus C0, so this will be C0 over 2. This one will be minus C2, which become negative, over 3. 3 times 2. This one will be negative of this, negative and negative become positive, C0, 4, 3, 2. And so on. And then you end up, this now is converging with the other one, right? And then you end up with this. You end up with a general expression for Cn. Cn will be minus 1 to the power n, C0 n factorial. Okay. So I basically did this twice. One with a more explicit notation, the other one with a more concise notation. Any questions? Some students find this stuff pretty hard. How are we doing? Okay, so I am going to.
Wait, so sorry, quick question.
Yes.
So when you're solving like a power series, is that y equals the summation of like Cn x to the n? Is that always going to be like the like a parent function that we use?
Yeah, that is like we assume the solution can be represented in that way. So at the end, okay, maybe I should write one more line. So at the end, after this, so my answer will be, because remember the beginning, write this one. Okay, maybe I just be more explicit. Write the solution. Write the solution as this. Okay.
Okay, so if it was like if what we were solving had like a y double prime, we would just derive that. Okay.
One more time. So most of the examples that we're going to do in the next section are going to be second order.
Okay.
So that's why it's good to be able to manipulate this stuff. Otherwise, it's a lot of writing. So at the end, so you get my Cn, right? So the solution is now y equal to this. Summation Cn, this is my Cn, and x to the power n. And this is the answer. Usually this cannot be put back into as an elementary function in closed form. It just happened to be, this problem is especially simple, just for illustration purpose. And it turned out to be this guy is e to the power minus x. Usually we can do this last step. So don't worry that if you get to a series and you don't recognize what function it is. Sometimes it's not even possible to recognize it. Most of the time. Are we okay?
Oh, so you don't think it's okay if we just leave our answer as a series?
Shelby, I cannot hear you well. Can you say it? Shelby? Are you saying something, Shelby?
apparently not. Okay.
His mic broke, and yes, he said he was saying something.
Oh, his mic broke. Okay. Okay, so we'll just keep going. Okay, so when he come back, if you have a question, you can use chat, Shelby. Are you using chat?
He asked if it's okay to leave the solution as a series.
Oh yeah, yes. The answer is yes, Shelby. Okay. Yeah, it's
He
okay.
says, okay, thank you.
Okay, so we are going to practice. We're going to practice this replacement technique. Okay. Sorry, the marker is making this noise. Oh my God, single power series. Okay, so we are going to do some of this. This may be too easy. It looks exactly like the one before. Okay, so let's do this. Okay, this really look exactly the same before. So what should we do? So we need to change this guy to x to the power n, right? So we should do a replacement for this part, the first part. Replace n by
n plus 1.
by n plus 1. Okay, so we'll have summation n plus 1 equal to 1, infinity, n plus 1, cn plus 1, xn plus 1 minus 1 minus summation. Now, this second one, you don't do it. So that you line up. Okay, so now this becomes 0 to infinity, n plus 1, cn plus 1. Okay, I just write it out. Okay. Now you can combine this because these two look the same now. You can combine these two together as one single summation. Okay, this is really the same as before. Not really that exciting. So we do something which is a little bit more exciting. How about that? Okay, so we do another one. Okay, so let's work on this guy together. Okay. Some of you may recognize this already. This one is probably coming from the second derivative, right? So Sylvia, you are pointing that out. This one is the second derivative of the original series. So what do we do?
And n plus 1.
That's already nice. Those guys are already nice. So what do we do to the first term?
Replace n with n plus 2.
Replace n by n plus 2. Okay. All right. So this guy become okay, I'm gonna try to not write so much, so I'm gonna single that out, replace n by 2. So this guy n plus 2 equal to 2 infinity, n plus 2, n plus 2 minus 1 is n plus 1, cn plus 2 xn. Is it okay? You guys follow that?
Yeah.
And then n plus 2 equal to 2 is the same as n equal to 0. Are we still okay?
Yeah.
Now here, I still have to subtract. I have to subtract this way. So now I end up with this. Now, when you combine them, you need to be, so this is nice. This xn is nice. They all line up. Now, but you need to be a little bit careful. You need to be a little bit careful. Because here, this one start with 0, this guy start with 0, this guy start with 1. Can you guys see that? You guys know what I'm talking about?
Yeah.
Yeah.
So we have to single out the case n equal to 0. Okay, the case n equal to 0 need to be singled out because I'm going to think of it like this. When n equal to 0, what happened? For this term, this guy n equal to 0. 2 times 1.
1 times whatever else.
C2?
Yeah.
2C2? Can you guys see 2C2? That's the first term.
Yes.
Plus summation. Now because I peel off that term, so now I have this. Okay. Now this one I just copied. Plus. Here I also have to peel off something here. So what do I peel off?
Do you just plug in that n equals 0, so it's just C0?
Very good. Cynthia. Now, we basically special case these two terms. Okay, we special case it. So you have 2C2 plus Z0 plus. Now this can be, all these other ones can be combined into one single summation. Is it okay? I'm sorry, I kind of run out of space. The x to the power n. This x to the power n is supposed to be squeezed into here. Okay. How are we doing, guys? Is it hard? Are we doing okay? Let me see whether I can find one to practice more. They are all very much the same though, so they are all very similar. Oh, maybe do this one. Okay, we'll do this one. Okay, we'll do one more. Okay, we have a little bit of time left. Any question about these examples? These two. We're going to do a third one. You guys okay? It's good to get this technique under control, okay? Because we're going to use it again and again later. This manipulation of the indices. So on Thursday, we have a test. So the test will be open at 12:45. And I think it will close at, I promise to give you 90 minutes, right? So it's closed at 2:15. I will be on Zoom in case you have questions, but you don't really need to be on if you don't want to.
Thank you.
Okay, let's work on this one. You want it to be involve x to the power n only. Okay, so here I have an n minus 2. So for this guy, so basically two parts. Okay, so this first part, we're going to do some replacement. This one will do some other replacement. So what do we end up with? What kind of replacement at the big here? N equal to
N plus 2.
N equal to n plus 2. Okay, so I'm going to try to maybe potentially skip some steps. Maybe you can follow it. N plus 2 equal to 2. That means n equal to 0. Is it okay? The first part, I did the first part. So here, replace n by n plus 2. How about here? Replace n by what?
N minus 2.
N minus 2. N minus 2 plus 2 is mixed. So now it's n minus 2 equal to 0 to infinity. N will be from 2 to infinity. Do you guys follow that?
Wait, sorry, could you repeat that again?
So, okay, so there's another step here. Replace n by n minus 2, right? Is it okay?
Yes, yeah.
So n minus 2 equal to 0 is the same as n equal to 2.
Yes, okay, got it. Thank you.
Okay, no problem. Okay. How do I combine these two? Now they are nice, both line up. But this has more terms. This guy has 2 more terms than this guy. Okay. So we have to special case those. So when n equal to 0, you have C2 n equal to 0. Sorry, 2C2, 2C2 x to the power 0, which is a constant term. Plus when n equal to 1, it's going to be 3 times 2 C3x. Now it's 2 to infinity. Right here, summation, n equal to 2 to infinity. It's 1 Cn plus 2 xn plus this guy. Now this last two terms can be combined because they have both of them is x to the power n, and both of them start at the same place. Is it okay?
Quick question, Professor. Is that a x to the n or c to the n on the second line of the second to last one?
This one?
The one before it.
This one?
Down to the right a little bit more. Yeah, is that a c to the n?
X, it's an x.
Oh, okay. Are there's like missing parentheses or something, or is that also c n plus 2x to the n?
Is there x to the n term supposed to be there?
You mean here? Down here?
Oh, wait. Oh.
Left, right?
No, in the very last summation.
Yeah?
Yeah.
This one is a c. Cn plus 2. This guy come from here. So this guy come from here.
Where did the x to the n term go when you combine them?
Oh, I mess up. Because I mess up. Thank you. Thank you. Yeah.
Professor.
Yes.
So I understand when you replace it by n, you replace the n by n plus 2, and you replace the n by n minus 2.
Yeah.
But after that line, how did you? So you got 2c2 plus 3 times 2 c3x by plugging in n equals 0.
Yeah.
And
n1. This is n equal to 0. This term is equal to 0. This term is n equal to 1.
Oh, and then the next one's n equals 2.
That's why this one has an x in it. This
Oh, okay. I see what you did there. Okay.
Are we okay?
Yeah.
Wait, sorry. In the very last term that you have, where it says n plus 2, n plus 1, is there supposed to be a parentheses around from n plus 2 to the c n plus 2, and then adding the c n minus 2, or does it matter?
I just kind of messy. I think it's like this. This number n plus 2 times n plus 1 times cn plus 2, and then add to this. So I mean, you can see it like this. The way to see it is that this guy here is this one. Okay?
Oh, yeah. Okay, so it's just like being distributed.
Yeah, it's basically just common factor. Common factor of x to the power n, you take the x to the power n out. If you distribute this, you will get back that line. Is it okay?
Yes, thank you.
Yeah, just combine the coefficient for x to the power n. And it was confusing because I forgot the x to the power n here. It's good that Antonio saw that.
Because sometimes the parentheses look like a c or vice versa.
Yeah, I was kind of terrible.
Yeah. Or if like it's.
I was not kind of terrible. I was terrible.
No, it's fine.
Yeah, like this one here is the c, right?
Oh.
But then it looked like
Mhm.
parentheses. answers. I just too lazy sometimes. Bad enough. Any other question? I'm not going to do another example, okay? And we have just a little bit of time left. So you can ask questions.
This is on. It's not on the test, right?
This one is not. Today's stuff is not on the test. Will be on the final. There will definitely be a problem on solving this thing type of stuff using power series in the final exam. How do you guys feel about this stuff? Is it hard? It's not too bad, hopefully. It's just a bunch of techniques that you need to learn. And it's quite powerful, actually. Okay, a lot of times in engineering problems, this is how they do it. Together with the numerical methods, it's also very popular. Because the answer, a lot of times, there's no closed form solution. Okay, so if you don't have any question, we just end about 6-7 minutes early today.
I have
Okay, go ahead.
questions
Yeah,
for
we
like
have-
the test. So it starts at 12:45, and we have 90 minutes, and
Yeah.
it's 3 attempts for 5 questions.
3 attempts for each question.
Oh, for each question. Okay, all right.
Yeah.
And
So
it's only 5 questions then, or 6.
it's only 5 questions. Yeah.
5.
You actually have plenty of time, I think.
Okay.
Yeah, actually, do we get partial credit on any of the questions, or is it just like hit or miss?
Unfortunately, it will be hit and miss. So if after you submit the whole thing, if afterwards, okay, you believe you're really close to the answer, but just type a little bit stuff wrong or something, okay? So right afterwards, though, don't wait a day or so, okay? Right afterwards, you're welcome to take a picture of your work and send it to me, okay? And then you say that, oh, I just forgot this. I forgot the stupid plus C thing, the concept. Okay, and it passed wrong. Take 20% off me. Okay. Then I'll take a look at your work, and then I also can check back your previous answer to make sure that that's indeed the case.
Yeah, because sometimes WebAssign like marks the answer wrong when it's still like right, just written differently. And that could get a little bit tricky, I guess.
Yeah, a little bit tricky. In the final, I probably won't do the same thing in the final exam. In the final exam, I probably will go back to pencil and paper, and you guys submit it through Canvas as a PDF file or JPEG file. Okay.
I see.
I think then I can give partial credit.
Yeah,
I know you already gave some extra time, but like I think some, or at least for me, it's kind of hard to like type in the answers and just writing it down, especially if it's like a really long expression. Do you think it's possible to get just like a little bit more time, like 15 minutes or so, or?
I already give another 15 minutes, and it's not that many questions. It's only 5 questions, right? You have like 18 minutes a question.
Yeah, that's fine. I guess
it's quite a lot. Yeah. So I probably would change the format on the final exam. I mean, this is good for is in some sense good because I don't have to grade it. In some sense, it's not too good because I cannot give partial credit. And so I actually in the linear algebra class, I'm not doing this on the second test. I'm actually doing pencil and paper, and I'll grade in Canvas. So I'll see how it works. It probably will work out better. Okay. Any other question about the test or about the lecture?
Did you have office hours today?
I'm supposed I can have office hour if you want to ask me questions. Do you want to ask me questions today?
It was like personal questions on the study guide. but
Okay.
I can wait. Like,
No, I mean, it's up to you. I mean, if you want it, I will do it. I have sent out the link for the office hour, right? And you can, do you have that email? Or
is it a separate Zoom session or is this?
it's a separate Zoom section.
Oh, it's a separate
If you
one.
want, you can stay on this one too. I mean, I don't think I have any requests from other students on office hour. If you want, you can just stay on this one, and I can just help you.
Yeah, I mean, if no one else has any questions, I can just ask it, I guess.
Okay. So anything else from other people? Okay. In that case, if you want to stay on and ask questions, you can. Shelby is going to ask me some questions. Okay. It's up to you whether you want to stay on.
Thank you, Professor.
Thank you.
Okay. You're welcome. Bye. Bye, everyone.
Thank you, Professor.
Okay.
Thank you.
Okay. Bye. Okay. Shelby.
Yeah, it was, well, I had a hard time on like a few study guide questions. I was wondering maybe if you were able to do it, I can see like the right way to do it, you know?
No, I don't want to do the whole study guide question for you though. Please,
Oh,
you need to
yeah,
be
yeah,
more
no,
specific.
it was just less, well, let me see.
Tell me which question.
It was the section 4.4, number 15 and 17.
Okay.
It was like, I was doing so many derivatives and the expressions were getting like super long, so I wasn't sure if I was even doing it correctly to like begin.
Section 4.4.
Yeah.
Yeah, undetermined coefficient. That's, yeah, it's very hard. It's very long, very tedious.
Yeah, and I like double checked everything and I still wasn't getting the right answer. So okay, let me see. Yeah. Like I can screen share
Okay.
screen share my work.
Okay.
If you are able to spot any mistakes, you can just tell me. Like,
okay. Yeah, okay.
Oh, you disable screen sharing.
Oh, I disable it. Oh, okay. So maybe you can tell me what do you do first.
Yeah, sure. I'll just tell you then. All right. So it's number 15, right?
Yeah. I mean, your numbers may be slightly different, but
yeah. So YC is equal to C1 cosine X plus C2 sine X.
Okay.
Because M is equal to plus or minus I.
Okay. And
then YP is equal to AX plus B cosine X plus AX plus B sine of X.
yeah, that's wrong.
But then there's a repeat, right? So you got to add an X to both the expressions. I think.
Yeah, okay, that's fine.
And then I did the derivative of that and the second derivative, and then plugged it back into the equation to solve for the coefficients.
It should work. I mean, whatever you get, okay, whatever you get, if it's not right, you can actually check. So it's probably just a matter of because you do the product rule, there's too many opportunity for mistake. That's probably all it is. Oh,
yeah, so I mean, I
see, okay. AX plus This can be right. Is that what you have?
Well, I used ax plus b for both of them. Are they supposed to be different?
I don't think you can do that.
Yeah. Okay. That might, because I got a equals 0, and then that doesn't let me solve for b, and like it was kind of weird.
Okay.
All right. No problem. What about for number
The same
17?
on 17. You said 17?
Yeah.
You probably have the same issue. Do you?
I'm looking at it right now. So for when you find the repeats, you have to distribute each term first, and then you can check for the repeated coefficients, or is
You
that
don't have, you're saying why do I multiply this in? Are you saying this?
Yeah, but you have to like you have to first distribute everything first to see if there's any repeats, right? Is that how it works?
No. I mean, because of the repeat, without the x will be a repeat. Without the x will be a repeat. That's why you put the x there. Once you have x, you will not have any repeat.
But you multiply x by everything, not just b.
Yeah, the whole thing. Yeah, the whole thing. Yeah.
Okay.
The whole thing. And I multiply it in because I don't want to do really complicated product rule, then it's already bad enough. Okay. So after I multiply in, at least this doesn't look as bad.
Oh, for 4.6, number 19.
Okay.
Yeah, I pretty much followed the formula, the u1 prime and u2 prime, and I still didn't get. I got like one part of the answer right, but not the other part.
Did you divide by 4 right at the beginning?
What was that?
Did you divide by 4 right at the beginning to put it in the standard form?
Yeah, because that's where the Wronskian is equal to 1, but yeah, the f of x is divided by 4, x e to the power of x over 2 over 4.
Okay. So what are your y1 and y2?
Let me see. Let me try and find it. Yeah, you can factor out like e to the x over 2 and e to the negative x over 2, and those become 1.
So this become the Wronskian is minus 1. Okay, I'm going to factor out some of this stuff then.
I think it's positive 1, right?
I mean, the way I do it, I mean, you might have swapped this too. I don't know. The way I do this is like, so you can get the answer?
No, I checked and I still. Wait, this is 4.6. Well, so after you, well, for the Wronskian, did you get 1?
My Wronskian is minus 1. My Wronskian is minus 1. What is your y1? Is it the same as mine?
E to the negative 1 over x over 2?
Or do your y1 and your y1, y2 and my y1, y2 are swapped?
Does that matter, or?
Yeah, the Wronskian will be negative of mine. It will be negative of mine.
But does that affect the final answer or no?
No, it does not.
It doesn't. Okay.
It does not affect my final answer. You get the u1 prime and u2 prime. Did you integrate it?
Yeah, I did it by integration by parts, and yeah, yeah.
So why don't you email it to me?
Yeah, I mean, because if I could screen share, I could show you pretty easily, but.
Well, let me see whether I can enable your screen share then. How do I do it?
Let me see. It says disable screen sharing.
Okay, I can just let you share then, okay?
Yeah. Yeah, I got it. Let me just.
It's okay now? Are you able to share now?
Yeah, I'm gonna do it through my phone actually. Can you see my phone?
Yeah.
All right. Okay, so see, I mean, this is the equation. Divide by 4 first, so that's the f of x. And then those are the y1, y2. The Wronskian, I got 1, because that becomes 1, and that e to the 0 is 1.
That's fine.
And then this is the formulas for u1 prime. I integrated that, integration by parts, and then that pretty much led to this result for u1. Is that correct?
I mean, I can't really go that fast. I mean, it's
yeah,
a lot.
sorry.
There's a lot of details. I mean, but the method seems correct. I mean, unless you do the integration by part incorrectly. And u1 prime is u1 prime. You use the formula, right? Negative.
Yeah, negative.
Negative whatever. I forgot.
Yeah, negative y2, I think.
Over w.
Yeah, and that's w, the whole thing right here.
Negative y2.
And then w is this one.
That's f of x.
Yeah, but w is just 1.
Negative y2 f of x.
Yeah.
Okay. And u2 prime, and u2 prime is what? Where is the u2 prime?
It's
y1.
e to the negative x over 2 times w f of x.
Okay.
And then that one's just an easy integral. And then this is like the answer that I came up with.
So can you go back to the earlier one? Why do you need integration by part? Where do you use integration by part?
Right here.
Hold on, just stabilize the phone. I mean, it's very difficult to read. It's jiggling.
All right.
Negative y2. Okay. Negative y2. I see. So you have an e to the x. So x equal to the x. Okay.
Yeah.
X e to the x. So where does this x squared come from?
Which one?
This x squared. There's an x squared there. Around there.
I crossed that part out because that's not right. I did it like over here.
Okay. I don't know if you have to take a look at that, check it, but it seems okay. So
yeah, and then
so what do you get at the end?
This is the answer, but only like this part was correct or something, or this part. I'm not sure.
Okay, I know what's going on now. So you have the did you find the is this an initial value problem?
That's the thing. I just saw that. I don't think I saw that earlier.
Yeah, you have to find the C1 and C2, right?
Yeah.
Okay.
Is that so? You just solve for C1 and C2, and that's it?
Yeah, I think so. Assuming you didn't make any other mistake.
Okay. Oh, okay. All right. Yeah, I'll do that again. But just one last like conceptual thing, like for section 4.9, you know, where you like eliminate x or y first.
Okay.
Does it matter which one you do first?
It doesn't really matter. Depends on the problem. Some problem it will be advantageous to do one rather than the other one. But the general method doesn't matter. The general method.
Because for number 3, when I eliminated, I think I eliminated x first, I got a completely different answer than what was the right answer. But when I eliminated the other variable first instead, I got the right answer.
But the answer, sometimes both answers are right. Okay.
Yeah.
If your C1 and C2 are in the function x, then you relate. Okay, let's say it depends on whether you want to write it. So you have C1 and C2, which is for x, C3 and C4, which is for y. It depends on how you relate it. You relate C1, C2 to in terms of C3, C4, or the other way around. You can do it either way. So the answer doesn't have to look exactly the same as the one in the book.
So it could look different.
It can look different.
But it's not like. What was that?
Whatever answer you get.
Yeah.
Whatever answer you get. Do you have a C1 and C2 or C3 and C4?
Oh, I did it with C1 and C2.
And is C1 and C2 for X or for Y?
For both of them.
Right, but for both of them, one of them is just C1, C2. The other one is some expression of C1 and C2. So here's what I'm trying to say. Okay.
Yeah.
Okay. I don't know whether you know what I'm saying. Can you see my board or not?
Yeah. Hold on, I gotta stop this.
So sometimes your solution can look like this, okay, potentially, but this is the same as this other one. So both of these are the same. So basically, this guy is saying that this coefficient is 4 times this coefficient. This one is half of this. Okay, if this guy is 4 times that, that guy is 1/4 of that, and this guy is twice of that. It's probably something like that that is happening there.
Yeah, I remember seeing that in the notes as well. I'm just trying to see real quick, like. Yeah, because I mean, for number 3, I was just able to plug it back into the original equation.
And it works, and it works.
Yeah, and it worked.
And it works.
But yeah, but the answer on the textbook was
I'm saying the textbook is not easy for the textbook to give you all possible forms of answers.
okay.
The software is probably smart enough to notice that.
Yeah, because I did it, so I eliminated X first and I got a different answer, but when I tried it by eliminating Y first, I got the right answer, as the same answer as the textbook.
I think that it's probably one case will get this, the other case will get that.
I see, okay.
Both of them are right.
All right. Yeah, and that's about it. Then I'll just email you my other questions because it was just from the notes, and it'll be easier to send you the photos and stuff, if that's okay.
Okay.
Yeah, awesome. Thank you.
Okay, you're welcome. Okay, anything else from other people? Okay, so see you guys. Okay, bye.
Have a good one.
Bye.